Hello everyone, I'm Martin Gubri and I will present you the paper called LGV, Boosting Adversarial Example Transferability from Large Geometric Vicinity. LGV in a nutshell is an adversarial attack that improves the transferability or the generalization of adversarial example by simply attacking models that are collected along the SGT trajectory with a constant high learning rate. It does beat all combination of four state-of-the-art technique by exploiting the geometry of the weight space to find flatter adversarial example in the feature space. A bit of background now. Adversarial examples are worst-case distributional shift, where carefully crafted imperceptible perturbations are applied to inputs in order to create large changes in output. A phenomenon called transferability was shown, which is the equivalent of generalization for adversarial examples, where an adversarial example against a model is likely to be also adversarial against another model. And this could be used for black box attack, where we want to target an unknown model using a surrogate that we know in white box. We first motivate our approach by showing that applying random direction in the weight space from a pre-trained model does constantly increase transferability, whereas random direction applied in the feature space during the attack does not. Based on this observation, we can show that the vicinity in the weight space is relevant for transferability. The intuition is that examples that are adversarial against a local ensemble of DNN are less prone to overfitting a single set of weights. Based on this insight, we propose LGV, which first starts by collecting models during 10 epochs with a high constant learning rate. Once we have collected the model, we apply classical iterative attacks on one model per iteration. Despite this simplicity, LGV is very effective, and it does beat alone all combination of four state-of-the-art technique by quite a large margin. Now we want to ask, why do weights collected from a vicinity help to attack a model from another vicinity? We identified two keys. The first one is that LGV does produce flatter adversarial examples, and the second one is that LGV subspace embeds geometrical properties that are relevant for transferability. Inspired by the literature about flatness for natural generalization, we developed the surrogate target misalignment hypothesis, where flatter adversarial examples may be more robust to misalignment between the surrogate and the target, and thus may transfer better. First, we show that LGV does collect models in flatter region of the weight space using three different techniques. As a result, LGV produces adversarial examples flatter in the feature space. Here we produce a disk defined by 3 points, a natural example, an LGV adversarial examples, and a baseline or one DNN adversarial examples. And we can see that the LGV adversarial examples is much flatter in the surrogate loss. At the same time, LGV appears particularly well aligned with the target where the two loss contours are similar shape which appear shifted. And these observations are coherent with our surrogate target misalignment hypothesis. We consider the weight subspace defined by deviation of LGV weights from their average. And we show that this subspace is first densely related to transferability, or it is useful. Second, it is composed of direction whose relative importance correlates with geometrical properties, or its geometry is relevant. And third, useful when shifted to other solution, or its geometry captures generic properties. In conclusion, LGV is simple yet effective to enhance black box attacks. Overall, the improved transferability of LGV comes from a geometry of the subspace formed by LGV weights in a flatter region of the loss. The paper, code, and poster are available online. Thanks a lot.